In this video, I'm going to cover the following learning outcomes. Let us follow the following video. The wave transfer energy from one place to another, but this without transfer any matter. For example, the light wave can come from your mobile to your eye without transferring any matter. Also the sound wave. So here, this is a displacement distance graph. Y-axis represents displacement and x-axis displacement distance. The crest is the highest point of the wave. So this point is crest, and this point is crest, and also this point is crest. The minimum point or the lowest point is called the trough. So this is trough, and also this is trough. Wavelength is the distance between two adjacent crests or two adjacent troughs, denoted by lambda. So the wavelength, it is the distance between two adjacent crests. Then remember that displacement distance graph, we can deduce the wavelength. What about the other graph? It is displacement time. So y-axis is the displacement and x-axis is the time. In that graph, we can deduce what? The time period. It is the time of one oscillation. So the time taken for one complete wave is called the time period. The frequency, denoted by F italic, is the number of waves sent out each second, the number of waves in 1 second. We have a relation between the frequency and the time period. This relation is that the frequency equals 1 over t. Remember, the frequency measured in hertz, the time period measured in seconds. Remember this rule, waves transfer energy. Actually, not any waves, the progressive waves. So the progressive waves transfer energy without transferring matter. Energy also depends on the amplitude. The bigger amplitude, the more energy. Actually, the energy, denoted by E, proportional directly to the amplitude squared. Now let us talk about the difference between transverse wave and longitudinal wave. Transverse wave and longitudinal wave. What is the difference between them? In transverse wave, the oscillations are perpendicular to the direction of energy transfer. So the particle vibrates up and down. So the oscillations up and down or perpendicular to the direction of energy transfer. And see, it's up and down. So this is the transverse wave. What is the example of transverse waves? Any electromagnetic waves like light, radio wave. Okay? Now, longitudinal waves, the oscillations that are parallel to the direction of energy transfer, forth and back. So here we have compression, rarefaction. The distance between two successive compressions is the wavelength. The example of longitudinal wave is the sound wave. Here you can see we have here crest and the crest. So the distance between two successive crests is the wavelength. The example of transverse wave is light. Longitudinal wave, the particles carrying the wave move back and forth along the direction of propagation of waves. Here you can see this is compression, this is rarefaction, this is compression. So the distance between two successive compressions is the wave length. Now let us talk about the wave speed. The wave speed is the speed at which the wave travels. Now, for one complete wave, this is one wave. What is the distance traveled? The distance traveled by one complete wave is the wavelength. What is the time taken by one complete wave? So the time is the time period. We know that the speed, denoted by v, equals the distance over time. Now the distance is lambda over t. But we know that 1 over t is the frequency. Then the speed equals lambda multiplied by the frequency. The speed measured in meter per second, lambda in meter, frequency in hertz. Then this is the formula. V equals lambda times f. We can draw triangle to represent this formula. V equals lambda multiplied by f. From this triangle, we can get lambda frequency or wavelength. Remember, very important note about the speed. Here we have the speed related to one medium and related to two different mediums. Medium means what? Solid, liquid, or gas. In the same medium, the speed is constant. So in the same medium, the speed is constant, unchanged. It means that the wavelength is proportional inversely to the frequency. When the frequency increases, the wavelength decreases. So in the same medium, the speed is constant. So the relation between lambda and the frequency is inverse relation. In two different mediums, the speed is not constant. The speed changes. V is changed because it depends on many things like the density of the medium. Because the speed here is unchanged, is changed, what will be the constant? The constant in the relation V lambda f, V equals lambda f, is the frequency. So, but the frequency is constant, unchanged. Why? Because it depends on the source of wave. It depends on the source of wave. Then the relation between lambda and wave speed is direct. So lambda proportional directly to the speed. So remember, in the same medium, the speed is constant. In different medium, the frequency is constant. What is the relation between lambda and the other quantities? Lambda is proportional inversely to the frequency in the if the speed is constant, but lambda is proportional directly to the speed if it is two different mediums. You can see here the speed of light in air is more than the speed of light in glass. So the speed in air, V, is big, then lambda also is big or long. But the speed in glass is small. So lambda also is small in glass. Then remember, lambda depends on the speed of wave. Rebel tank. What is the rebel tank? It is an instrument, contains water and generator of the waves, and down this container we have a paper and light. So from when the light is switched on, we can see the figure of the wave. So we can demonstrate all the properties of waves by using the rebel tank. So we can demonstrate the reflection, refraction, diffraction. Here you can see this is the water tank and this is the reflection. Here, this is the reflection on the barrier. You can see that the wavelength the same, but the speed changes its direction. So this is the reflection in the rebel tank. This is the reflection in the rebel tank. The angle of incidence equal the angle of reflection. Here you can see this is the angle of reflection, angle of incidence. This is I, and this is the angle of reflection. The two angles are equal. So this is the incident ray and this is the reflected ray. So the wave front here is a line joining adjacent points on the wave that are all in a step with each other. The wave front are the points of crest. Now, what about the refraction? Let us we see the refraction in the rebel tank. Refraction in the rebel tank. You can see here the wavelength changes in refraction because the speed of wave changes. Then you can see the change in the wavelength in the refraction. Now, this is the refraction. Here we have deep water and shallow water. We need to understand what we mean by deep water and shallow water. Here, this is in the deep water. You can see the wave pattern on the base of the pool. So the wavelength is more wavelength, and the speed is more in the deep water. In the shallow water, because the friction between the water and the seabed, so the speed of wave decreases. Then in shallow water, the speed of wave less than the speed in deep water. So this is the refraction in the rebel tank. Refraction occurs when the speed of wave changes. So you can see here the wavelength. This is lambda, but this is in the deep water. It's more than lambda in shallow water. What about the diffraction? Let us we see the diffraction by using the rebel tank. This is the diffraction in the rebel tank. When the wave passes through a gap, it will be diffracted. It will be converted from plane wave to be circular waves. So this is called diffraction. Diffraction when waves spreads out as it travels through a gap or past the edge of an object. The sound waves are diffracted as they pass through a doorway and open windows. This is why we can hear a person around the corner even though we cannot see them. Now this is the diffraction. The diffraction depends on the relation between the gap width and the wavelength. So this is the wavelength, lambda, and this is the gap. When the gap width equals the wavelength, then the diffraction will be occur. What is the diffraction? In diffraction, no change in speed, so the same speed. No change in the wavelength, lambda is the same. No change in frequency, just a change in the pattern or the shape of wave from plane waves to circular waves. So remember, in diffraction, the size of gap affects the diffraction. Let us we see that exercise. It contains questions from past paper. Question number 1. The frequency unchanged because the frequency depends on the source of wave. Then the answer of this part is unchanged. We say it's unchanged. What happened to the speed of wave? The speed reduced. So the speed reduced. Why? Due to the friction, due to the friction, okay, between the waves and C band and C band. So the speed is reduced. Now, next, what happened to the wavelength will be reduced. You can see that because the speed and lambda are proportional directly. If the speed reduced, also the wavelength will be reduced. Why? Because the speed proportional directly to lambda. Now, the waves have a speed of, now this is a given, the speed of wave v equals 0.12 meter per second. In the deep water, wave crests are 0.08 apart. Wave crests, the distance between two crests, it means the wavelength. Then we have lambda. So lambda equal 0.08 meter. Calculate the frequency, stating the equation. Of course, the equation is that V equals lambda F. So the equation is that V equals lambda F. Rearrange the equation to get the frequency. So the frequency equals V over lambda. V is the speed of wave, 0.12, divided by lambda, 0.08. The answer is 1.5. Remember the unit of frequency is hertz. Shallow water, so the wavelength decreases. You will need to use your ruler to do this. Now we use the ruler, but here just I give you the way. So by using the ruler, we're starting from this point A, and then draw line, and then from this point draw another line parallel, but you know that it must be less in wavelength, then we draw this to be less wavelength, then the wavelength must be less. It's like this here, it's like this, must be parallel, and then complete another two waves. All the waves must be parallel and they have the same distance wavelength. So they are parallel. You can see they are parallel, but the wavelength here, lambda, is less than lambda in the deep water. So this is the way, but we use the ruler to draw that lines. Next question, question number 2. A wave passes along the surface of water in rebel tank. Describe the motion of molecules. Molecule moves up and down. Or we can say the oscillations, or we can say oscillates, perpendicular, right angle, perpendicular, two direction, of wave energy. In the figure, sketch the pattern of waves in the region to the right of the barrier. Now, just we put here the center of the gap, use the compass and draw circles with that center. But all the circles, they have the same center, and the distance is the same as in front. Then we draw semicircle, and then with the same wavelength, semicircle, with the same wavelength, semicircle, okay, with the same wavelength, semicircle. Remember, the wavelength in front must be the same as the wavelength at the back. And the center of all circles is that, at the center of the narrow gap. State the process by which waves arrive at the point B. Of course, this is diffraction. Next question. Then we have lambda, 1.4 centimeter. Travel at speed, so we have V, 12 centimeter per second. Calculate the frequency. It's easy question. We use the formula V equals lambda times F. Now, if the speed in centimeter per second and lambda in centimeter, you don't need to change the units because the frequency will be in hertz. Then the formula is that the frequency equals V over lambda. V is the speed, 12 over lambda, 1.4. The answer is 8.57 to 3 significant figures, and the unit will be hertz. A water wave in a tank travels from a region where the speed of wave is faster, it's deep water, into a region where it is lower. The following figure is 1/4 scale. So take care for this word. It's 1/4 scale diagram that shows the wave fronts in the region where the speed is faster. Look at this. He said the scale, each 1 centimeter represents 4 centimeters. So 1 centimeter in the scale drawing represent 4 centimeters. Take the measurements from the scale diagram in the figure to determine the wavelength of the water wave as travels in the faster. Now we use a ruler to get the distance between two successive wave fronts. By using my ruler, it's about 0.6 centimeter. Then this is the distance in the scale in the diagram. So 0.6 multiplied by 4, we convert it. So 0.6 multiplied by 4, it's 2.4 centimeter. Then the actual wave length is 2.4 centimeter. Okay, so to determine, so lambda equals 0.6 multiplied by 4, it's 2.4 centimeter. The speed of the wave in the faster, in the same region, is 0.39 meter per second. Calculate the frequency. Now we have different units. The speed equals 0.39 meter per second, but the wavelength, it's 2.4 centimeter. Then we have to convert centimeter to meter. We divide it by 100. Then 2.4 divided by 100. So the answer is 0.024 meter. Now we can calculate the frequency. The frequency equals V over lambda. V is the speed, which is 0.39 over lambda, 0.024. 16.25, and the unit is hertz. Next question. In the figure, draw lines that indicate the positions of the wave fronts of the water in the shallow region. Now, in the shallow region, what will happen to the wave front will be decreases. Then we draw lines, but the wavelength will be less than 0.6. We can start from this point here, and then we draw parallel. You can see here. We have to use the ruler, and it must be parallel with the same separation, but the separation, it will be less than, the separation less than 0.6. You have to use the ruler, of course, and all of them must be parallel. Okay. Now, he said, in the figure, draw lines. Class, we finished. Now, next question. State, next, state what happened to the frequency of water waves as it passes into the slower, unchanged, because it depends on the source of wave. So, unchanged. The frequency unchanged. Next question, the following figure shows the displacement of particles in a water wave. Using the information in the figure, determine the wavelength. Now, what is the wavelength? This is displacement distance. Then the wavelength here, it is the length of one wave. You can see this point, it's 8.0. Then 8.0 what? Centimeter. Then the wavelength denoted by lambda, it's 8.0 meter. Next part, the amplitude. The amplitude is the maximum displacement from equilibrium position. The maximum displacement or the distance from crest to the center of the wave. It's 1.5 and the unit is centimeter. Then the amplitude denoted by A equals 1.5 centimeter. Next part. Now, so this is on the figure, complete 3 wave fronts for the waves in the shallow water. Now, I advise you to start from this point and then draw line and another line parallel to it, but with wavelengths less than. So remember, this is the wavelength in the deep water. This is the wavelength in the shallow water, it will be less. And the third one also, it must be parallel. All of them must be drawn by using the ruler, and they must be parallel to each other and the same separation. State the term for process at the boundary. It is refraction. So this is a refraction of waves because the speed changes. Now, next question. Next question. A student observes waves on the surface of water in a tank. The waves all have the same wavelength. The students measure the wavelength of the waves by measuring the distance, okay, between one peak and the next, between crest and the crest. Describe a more accurate method for determining the wavelength. Of course, we take more measurements and take the average. Then, number 1, measure more than one length. Measure more than one wavelength. One wavelength. Number 2, take the average. Take the average by dividing measurement by the number of wavelengths. The number of wave length that measured. So we take the average of many readings. Now, next part. The wavelength of the waves is 4 centimeters, so this is lambda, 4 centimeters, and the frequency is 6 hertz. What is the speed? If lambda in centimeter, then the speed it will be centimeter per second. So the speed equals lambda multiply f. Lambda is 4 multiplied by the frequency equals 6 hertz. Okay, equals 6 hertz. 4 times 6 equals 24, and the unit is centimeter per second. Now, next part of the question. The waves refracted, its speed will be reduced. So we write the waves are refracted. Its speed will be reduced. Will be reduced. Next question. A teacher demonstrates the behavior of waves by using water waves in a ripple tank. The following figure shows cross-section through part of water waves. Calculate the wavelength of the water using the information in the figure. Look, from crest to crest, this is the wavelength. So this is one wave, lambda. From crest to crest, lambda, lambda. It is a wave, one wave, lambda. From crest to crest, lambda, and so on. How many lambda we have, or how many waves? 1, 2, 3, 4, 5, 6, 7. Then 7 lambda equals what? Equals 18.2 centimeter. Then from this we can get the wavelength. Then wavelength lambda equals 18.2 divided by 7. The answer is 2.6 and the unit is centimeter. 3 students used stopwatches to measure the time taken for 50 beats. 50 beats, it means 50 waves. 50 waves. Okay. Now, that are the times. This is the time of the first one, the time of the second, and so on. On the line blue, each stopwatch state the time measurement. Now, this time in the first stopwatch is 17.24. The second is 17.14 second. The third is 17.16 second. Now, calculate the average. The average is the total divided by the number. Then we write 17.24 plus, in bracket, 17.14 plus 17.16 divided by 3. The answer is 51.54 divided by 3. So the answer is 17.18 seconds. This is the average. Calculate the frequency. Now, to calculate the frequency, here we have, okay, the time, but this is the time of what? This is the time of 50 waves. We said that. The time taken for 50 beats. Then this is the average time. This is the average time of 50 waves. Then 50 waves, 50 time period equals 17.18. From this, we can get the time period equals 17.18 divided by 50. The answer is 0.34 second. Now we can get the frequency because we know that the frequency 1 over time period. So 1 over 0.34, the answer is 2.91 and the unit is hertz. Lambda, the frequency equals, calculate the speed. It's easy. V equals the lambda multiply f. Lambda is 0.025 multiply f 2.4. The answer is 0.06 and the unit is meter per second. The following figure represents a wave on a string. Complete the sentences about the wave. Use words from the books. Now we have that words. The wave transfers what? Of course, transfer energy. The number of waves per second is what is, of course, the frequency. The distance between the point B and the point Q, it is the amplitude. So the answer is the amplitude. The distance between Q and R, this is Q and R, it is the wavelength. Wavelength. Now, the wave on the string is an example of transverse wave. Explain how transverse wave differs from longitudinal wave. Transverse wave vibrates perpendicular to energy transfer. So, transverse wave, okay, vibrates perpendicular right angle to the wave energy or the energy transfer. Now, the next question, the following figure represents a traveling wave at an instant in time. This is what? Displacement in centimeter, and this is the distance in centimeter also. Determine the amplitude. Now the amplitude is the maximum displacement from the center. It is 0.9. Then the amplitude is 0.9 centimeter. The unit is centimeter. Now, next part, the wavelength. Now, how many waves we have? Count with me. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 waves. What is the total distance of 8 waves? You can see here this is 10, then each one dash is 2. Then this point here, this is 1 dash after 110, so it's 112. Then 8 waves equals what? 8 waves equals 112. So 8 waves, the length of them is 112 centimeters. Then the wavelength equals 112 divided by 8 equals 14 centimeters. So this is the wavelength. Now, it takes 2 seconds for the source to emit the wave shown in the, calculate the frequency. The frequency is the number of waves in 1 second. We have 8 waves in 2 seconds. Then how many waves in 1 second? It is just 4. Then the number of waves in 1 second is 4. It means that the frequency is 4 hertz. The following figure shows a floating plastic ball attached by a long rope to the weight on the bottom of lake. A water wave on the surface of the lake causes the ball to move vertically up and down. Of course, this is transverse wave, and this is the direction of travel of the water wave. In the figure, indicate the wavelength of the wave. Label it with W. We can take this. This is the distance between 2 crests. It's W. So this is the wave. Determine the amplitude. The total distance from crest to trough is 24. Then the amplitude is half the total distance. So the amplitude equals 24 divided by 2 equals 12 centimeter. Part C, the ball reaches its maximum height 40 times in 60 seconds. 40 times in 60 seconds, it means 40 waves in 60 seconds. Calculate the frequency. Now, we have here 40 waves in 60 seconds. How many waves in 1 second? This is the frequency. Then we can do cross multiplication. So the frequency, the number of waves in 1 second, it's 1 multiply by 40 over 60. So the frequency equals 0.67 Hertz. Explain how the motion of the ball shows the water wave is transverse because the direction of travel is perpendicular to the direction of vibration. Now we can write here because direction of travel is perpendicular to direction of vibration. Next part. State another example of transverse wave, light wave or any electromagnetic wave. We can say light wave. This is example of transverse. Next question. The following figure shows transverse wave for distances A, B, C, and D are marked on the wave. State the letters that show the amplitude. Of course, the amplitude is A. State the meaning of term frequency. It is the number of complete waves produced by the source each second. Number of complete waves produced by source or by the source each second. Next part. A long spring is fixed at one end as shown in the following figure. The spring is moved towards and away from a fixed point repeatedly. The compressions and rarefactions on the spring at a particular time can be seen. So you can see here, this is the compression, this is this is rarefaction, this is compression, this is rarefaction, this is compression, this is rarefaction, and so on. State the type of wave in the spring. Of course, it is longitudinal. Next, state one other example of this type of wave, sound wave. Sound wave is good example of longitudinal sound wave. Now, use the scale to determine the wavelength. Now, here, this is the center of rarefaction. Now, what is the center of rarefaction? It's here. This is the center of rarefaction. So, this is 1 meter. Then we can say this is 10, 20, 30, 40, 50, 60, 70, 80. Then it's approximately 85 centimeter. So the wavelength, it is the distance between the center of rarefaction to the center. So this distance approximately 85 centimeter or 90 centimeter. So the wavelength is 85 centimeter or 90 centimeter, both are correct. Think of the question and then I give you the answer. See. Yes. Yep. The answer is A. Just I give you the answer. If you have any doubt, you can call me. Question number 13. Question number 13. Please be careful. The answer will be B. The answer is C. The answer is C. The answer is D. The answer is D. Question number 18. The answer is B. Next question. Question number 19. The answer is A. Question number 20. The answer is A. Question number 21. The answer is A. Question number 22. The answer is C. I hope you understand this video. Thank you.